Let's use friction to analyze this crate resting on a truck. So we have a 50 kilogram crate resting on the bed of a truck. I'll go ahead and note as I read the problem that my mass is 50 kilograms of my crate. And the coefficients of friction between the truck and the crate, so between these surfaces, are as shown here, mu k equals 0.3 and mu s equals 0.4. Now we want to find the frictional force on the crate when the truck is accelerating forward relative to the ground at two different speeds. I'll begin this by assuming, for part A, that my crate is statically sitting on the trunk as it accelerates. So assume the crate is static with respect to the truck. So it's moving because the truck is moving, but it's not moving with respect to the truck. In other words, friction is enough to keep it on there and accelerating with the truck. We'll do a free body diagram of the crate. So we'll start by drawing the crate. Here's my crate, has a mass, and then we'll have its weight acting down, mg. We'll have some normal force acting up. And then as the truck accelerates here, if the crate were to slide, it would be moving relative to the truck that way. So friction has to oppose that direction of motion and has to move this way. In other words, the reason this crate would be accelerating with the truck has to be because of friction. So the acceleration of the crate, if it's going to equal the acceleration of the truck, has to be because friction is dragging it along with the truck. All right, we have our free body diagram. We can now move on to doing Newton's laws. We'll start with y-directional. Sums of the forces in the y are equal to mass times acceleration in the y, where if this sits on the truck there, it's not moving up or down, so that acceleration will be 0. And we'll call up positive. So this tells me that my normal force minus mg is equal to 0. This tells me my normal force is equal to mg. That's often the case, but not always the case. For example, if we had some other force or some strap tying this down, we would have more normal force than just its own weight. But here, it's just its own weight, so we can plug in the 50 kilograms times the 9.8 meters per second squared, and we end up with a normal force of 490 newtons. We can now move on to our sums of our forces in the x direction. Go ahead and do this over here. Sums of the forces in the x are equal to mass times acceleration in the x. And here, the only thing acting is friction, and that's equal to mass times acceleration. We can plug that in, 50 kilograms. Assuming that it's accelerating with the truck, that's going to be 2 meters per second squared, which gives us 100 newtons worth of force. So the force of friction has to be 100 newtons. So what's the frictional force on the crate? Well, this says it has to be 100 newtons for it to accelerate with the truck and not slide on the truck. Is that possible? This is where we can check our assumptions. So we assumed that the crate was static. Let's check to see if we are able to actually exert that much frictional force. So we'll check the assumption. And we'll do that by looking at the maximum static frictional force. And I guess we could have tried to do this initially before making this assumption. So that's equal to mu Sn. So the most frictional force we could get is 0.4 times that normal force of 490, which means that we can exert a frictional force up to 196 newtons. This tells me that the actual frictional force that I found of 100 newtons is less than or equal to my maximum static frictional force. So that's good. That satisfies my assumption that my force is less than the maximum allowable, so this is perfectly fine. We can accelerate at 2 meters per second squared, and this crate will stay sitting on this truck bed. Lovely. How about for 5 meters per second squared? Well, for part B here, everything's the same, except for now, we have just a different acceleration. So this gives us that my force of friction is equal to 50 kilograms times now 5 meters per second squared, which tells me that I have 250 newtons worth of frictional force. This, when we check our assumption, is F less than or equal to my maximum static frictional force? No, it's not. 250 is not less than 196. So this can't be true here. So that means the friction has to be kinetic. And we can find that kinetic friction by using mu kn, and mu k is 0.3 times the normal force is the same, 490, which when evaluated gives us an actual frictional force, in this instance, of 147 newtons. With the same direction, it's still trying to drag this along. This raises an interesting question. Could we find the maximum acceleration that we could accelerate with while keeping this crate stationary? And in fact, we could. If we look back to what we had over here, we can apply our limiting case here and say that my force is equal to max, my force of friction. We can solve for this maximum acceleration in terms of the frictional force and plug in the maximum value here. So I can plug in my 147, actually, yeah, so you could put 196, there we go. So you can plug in the 196 there and find a maximum acceleration. We can also find, if we wanted to, what our acceleration of the crate is due to the frictional force that we get in part B. So we could plug in the 147 and get an acceleration of the crate. And you would see that the crate would be accelerating, but more than 2 meters per second squared, but less than 5 meters per second squared. So relative to the truck, it would be going backwards on the truck.